So let's now solve a practical problem of calculating mutual inductance. The problem shown here is a mutual inductance between an infinitely long wire, which is shown in red, and a loop shown in blue. And I've adopted the same color scheme here. So loop 1 is in blue and carries a current I1. Loop 2 is I2 and carries and is shown in red. And I2 is technically a loop because even though it looks like just a single line, this current does close at infinity and comes back and flows up from the bottom. So we do have two closed circuits here. So the first question we want to ask ourselves is which flux do we want to use or calculate? Because we have a choice. We can calculate phi12, which is the flux produced by coil 1 and observed over coil 2, or we can find phi21, which is the flux produced over coil 1 by I2. And that's where reciprocity is very handy because we can choose, one of these is going to be easier to calculate than the other one. The first one, phi12, is quite challenging because we need to calculate the B field produced by I1. That's going to be complicated because we have three segments making up the current over which I1 is traveling. So there's going to be three calculations to do there. And we need to integrate the B field over the area of loop 2. Loop 2 is an infinite line current going from z equals minus infinity to z equals plus infinity. So it's not entirely clear what we use for the loop area in that case. Consider the reciprocal situation where we excite the line current I2 and then try to find the flux generated over the triangular loop. That's a much easier problem to solve. So we're going to try to find phi21, which is produced by I2 over loop 1, the blue loop that we see in the diagram. To calculate the flux, we need to know the B field produced by I2, which we'll call B2. And B2 is actually fairly easy for us to work out because we have analyzed infinite line currents on the z-axis before using Ampere's law or the Biot-Savart law. So we can just write out the result here. If we're in free space, this would be mu naught times I2 over 2 pi r, where r is the radial distance from the line current. And this is technically in the phi direction. And if we were to use the right-hand rule, the B field produced by I2 would look something like this. And it's going to get weaker as we move towards the right. So if we're trying to find the flux over the blue loop, we can't just simply take B2 and multiply by the area of the loop because the B field actually gets weaker as we move from left to right over the triangle. So we're going to have to do an integration here. So let's write out an expression for phi21. We're going to have to integrate over S1, which is the triangular loop, the magnetic flux density produced by line current 2, as shown here. So the first thing that we should do is try to work in a slightly easier coordinate system if we can. And in this particular problem, loop 1, the triangular loop, lies entirely within the xz plane. So if you look at the sketch of B2, when B2 reaches the xz plane, it literally is going to be going through the loop like this. And looking at our coordinate system, that is clearly in the minus y direction. We have a right-handed coordinate system here, so the y-axis goes into the page. So our B field is in the y direction. So we might as well write that out here, the minus y direction, and change that unit vector phi hat to minus y hat. We can also change the radial distance in the denominator, which was r before, to just simply x, right? Because again, in the xz plane, the radial distance from the current I2 is simply x. So now we have an expression in Cartesian coordinates for B2. That means that we need to find a corresponding expression for ds1 in Cartesian coordinates. So let's have a look at how we can do this. Let's clear up some space on our loop just to make this a bit clearer, and think about what our differential area element should be. So an easy thing to do would be to draw a strip here, which I'll highlight, shown here. And this strip has got a differential width, which we'll call dx, right? And dx remains fixed, but as we move this little strip from left to right, the height of the strip varies. It's going to get taller as we move towards the left of the triangle, and it's going to become smaller as we move to the right of the triangle. So we can begin to propose an expression here for ds1. This is the area of this little strip that we have written here. So the width of the strip is dx, and the height of the strip, we'll call it z. So z is going to be the distance from the base of the triangle to some point. So let me write this so that it matches what we have sketched here. So for that particular strip that we wrote over here, z is going to be something like this. It's going to line up with the top of the strip. This is z, right? So we have the width of the strip, we have the height of the strip, and so the product of dx and z should be the area of that strip. Now we need to attach a unit vector to this, and the unit vector of this differential area element is going to point in the minus y direction as well. So we will put the y hat direction and put a minus sign here. So it's parallel with the B field, which is what we want because we want to eliminate that dot product that we see appearing in this expression for phi 2, 1. All right, so before we go too much further, we need to come up with an expression for z. So we can see that there's a 60-degree angle that is made in this triangle here. And looking at our triangle, we're going to have to define how does z vary with x. So let's draw a line down from the edge of the triangle, and let's define just a temporary variable here, x prime, which is the distance, the horizontal distance away from that corner of the triangle. So we see that from the line current to here is a distance d, and we know that the distance from the z-axis to any point in the x direction is just x. So we can define x prime to be the x position where the edge of the triangle is. So this position here is d plus the width of the triangle, which is shown as b, or maybe we should define it as b. It wasn't labeled in the diagram here. So this distance here is b. So this is x equals d plus b here. So for defining x prime, we start at the position d plus b, and then we subtract x, right? This is the new coordinate x prime. So if we then look at our triangle, we can define a relationship for the height of the triangle and the base of the triangle, because we know that the angle at the lower right corner there is 60 degrees. So tan 60 degrees is equal to the opposite side of the triangle, which is of height z, over the base of the triangle, which is x prime. So, and this is for x prime between 0 and b. So we know that if we evaluate the tangent of 60 degrees, this is root 3. So now we have if we rearrange this equation, we can write that z prime, z is equal to root 3 x prime, which is equal to root 3 times d plus b minus x, making the substitution that we had before. So now we can return to our expression for ds1 that we have up above. This is going to be minus y hat, and then we have root 3 d plus b minus x for x prime, or sorry, for z, and then we multiply by dx. So now we're ready to take the dot product between b2 and ds1. They are parallel because they're both in the minus y direction. So we can proceed to calculate phi 2,1. And recognize that this is going to be equal to lambda 2,1 because there's only a single turn for that triangular loop. So we need to integrate now the product of b2, and the dot product disappears, and we're just going to multiply this by root 3 d plus b minus x dx. There is no minus sign anymore because the two minus signs canceled out, and we're now integrating x from left to right. So x starts at d. If we look at the diagram, d is the left edge of the triangle, and we go to d plus b, which is the right-hand edge of that triangle. So now we're ready to proceed with this integration. There are a bunch of constants that come out of the integral. We have a mu naught, I2, root 3, and 2 pi in the denominator. We're integrating from d to d plus b. And we can rearrange the integrand a little bit as well because we're dividing by x. So we have d plus b divided by x and minus 1. And then the dx is common to both. So this is fairly easy to integrate now. We're going to have to break this into obviously two integrals and integrate each contribution to the integrand separately. So let's copy our constant down here. So the first part of the integrand, d plus b over x, we're basically integrating 1 over x times a constant d plus b. So that's natural log of x, and then we're evaluating it at its limit, so d plus b over d. And then we need to integrate the second part of the integrand, which is this minus 1, but that's very easy. That just integrates to x, and then if we evaluate it at the limits, the upper limit is d plus b, the lower limit is just d, so the difference between those two is just b. So we have this. And this is the final result for the magnetic flux linking the two devices here. So now we can find L21 by simply dividing out the current I2. So we basically get the same expression here, just minus the I2. And this is the mutual inductance. And again, I want to emphasize that this is the same mutual inductance if we had reversed the roles of the excited device and the observing device. And if you want, we could just call this the mutual inductance M. So this concludes our review of mutual inductance for a multi-inductor system.